Hello, everybody.
Hello.
Hello. We had the midterm exam on Friday, and it seems like I haven't completely looked into it, but from the submissions, the rate at which it came back, so I think it was not as long as earlier exams, so hopefully it went out well. Any comments directly, immediately you guys have? I haven't graded it.
Could we go over problem number 6?
Problem number 6. What was it about? Do you guys remember? Okay, just have one. Problem number 6. Let me see. I might have access here.
I think it was the work of friction down a slope.
Yeah, that one.
Work done by friction. Huh. Why doesn't it ring a bell? Give me a second. Okay, number 6. Determine the work done by the force of friction. Oh, yeah. Yes, so let me go over that. So how about I go here? So we are talking about an inclined plane. That's angle theta, and we have a mass m sitting here, and it is sliding down. Let's identify the forces first. Mg acting downwards, normal force acting perpendicular to it, and there is force of friction acting in the backward direction. So you would write your Newton's law as mg plus the normal force plus the force of friction. We are interested in using the work energy theorem. So you would say this corresponds to change in kinetic energy. The force of gravity, being a conservative force, can be expressed in terms of final and initial points using potential energy. It moves to the left because of the change negative sign. So that's change in potential energy due to gravity is equal to the work done by the normal force plus the work done by friction. First, you argue that the work done by normal force is 0, right? Because the normal force is acting perpendicular to the displacement all the time, so that's equal to 0. So the work done by the force of friction is equal to change in kinetic energy plus the change in potential energy due to gravity. So that's half mv final square minus half mv initial square plus mg h final minus mg h initial. The initial velocity is 0, that's equal to 0. The final height can be chosen to be 0. Like it is the relative height that comes into picture. So that's equal to 0. So you have half mv final square, so this is square, minus mg height h. Does that help?
Yes, thank you.
And I do post the solutions also, right? Hopefully, maybe it is not very clear, but still, just for your information, the homeworks were posted almost immediately or as soon as possible after exams. Okay, was the exam reasonable? Any comments on that? Nothing? Okay. Last time I could grade the exams before Wednesday. Hopefully this time also I will be able to, but surely by the end of the week, I'll surely do that. So, so that's about the exam. Going forward, we have a homework 10 that has been posted. It will be due on Wednesday, not the coming Wednesday, but the Wednesday, 1 week from Wednesday. After that, we will have 11th homework will be shorter, exactly like a few weeks before. This will be due on Monday. And the next homework will be due on 30th. So that's the last day of classes. And we will have final exam on it's May 6th. I looked up, usually you have to look up into a chart and find out when is the final exam. So this is what I found. So do check on it on your own and let me know if I'm making a mistake. So it's 2:45, 4:45. It is a 2-hour exam, but that doesn't mean that it will be double the length of what we have on a normal hour, maybe 1.5 times or so. So that's how I plan to do it. It won't be significantly long. It will be comprehensive. So this will be comprehensive. And that means that about 70% or 60 to 70% of what we covered before midterm 3 and about 25 to 30% of what we did after midterm 3. So that's how we will go about it. The quiz problem talked about rotational motion. Is it commutative or not? And what that means is that if you were to do rotations in different order, what happens? And one can analyze this on a textbook. So for example, let's say this is a calculator. Let me see if it is easy to do this on video here. So let me erase this to begin with. Okay, so what we want to do is that first, so this is the real X and whatever you guys are seeing. So that's X, Y, and that's your Z axis. So I'm going to keep this calculator here. First, we will rotate. So first scenario will be rotate about the Z axis. So that's your Z axis. And rotate it counterclockwise by 90 degrees. So that's what we can do. And then plus, right? So in the right order. And let us say after that you go about y-axis and you rotate it in this fashion. So that's your y-axis. So you rotate it in this direction. Okay, and then we will see what do we get. And the second case could be you do it exactly in the opposite order. First do the rotation about y-axis and then do the rotation about the z-axis. And the question is, do we get the same system or not? So let's see how do we go about this. So this is the calculator. When I rotate this about this 90 degrees, I get this. So the top of the calculator is facing in that direction. And now I have y-axis here. I have to rotate it in this form, right? So that's 90 degrees again. So the head is facing you with the face of the calculator facing to the right. So that means the face to my right while I'm facing the board, and head is facing you guys, right? Head coming out the board. And let's see if we can reproduce that again. So this is again the calculator, and now this time we want to rotate 90 degrees about the y-axis. So that's 90 degrees about the y-axis. And then we have to rotate about the z-axis by 90 degrees. That's here. So this time, head is to the left. Head to the left. And face is upwards, right? And clearly, that's not the same as what we had earlier, right? Up, so it's slightly out of the board. Face to the right, face to the up. So it's not the same. That's the idea. So that's the meaning of saying that rotation is not commutative. It matters in what order you do. And there are physical consequences of this when you do, especially there's a field of physics called quantum mechanics. These things become very relevant in that case. Okay. So let's go back to rotational motion. We started discussing rotational motion, and the first thing we talked about is rotational motion is with respect to an axis all the time. So rotational motion. We did motivate as to why we are studying rotational motion. Any motion of any object can be broken into translational motion of the center of mass plus rotational motion about an axis passing through the center of mass. So that's that motivates us to say that, okay, so we want to study rotational motion for a complete understanding of the motion of an object. Most of the time here, almost always actually in this course, because we have only 1 or 2 weeks to study this, we will keep the axis of rotation fixed. That means it will either come out of the board or it will be very clear where it is and it is not going to move around. Due to that, the rate of change, we are talking about changes, it's significantly easier. We don't have to worry about the change in the axis itself. Typically, in real life, there is a contribution to the motion due to the change of the axis itself, and that has non-trivial conclusions out there. But we won't have time to discuss that. So keep the axis fixed. So we discussed at length the axis is last time. The axis will be kept fixed. The axis of rotation will stay fixed. And we do lose a lot of richness in the problem. This is very much like saying if you're doing uniform velocity, you don't see a lot of richness in motion. Similarly, just because we have kept the axis of rotation fixed, we will lose a lot of information. But even then, we will have enough things to talk about. So let's think of a road, and we have a simple wheel rotating about it, and this is touching the road all the time, and there is friction, sufficient friction on the road that you can have perfect rotation, right? So, or perfect rolling, sorry. So every time the amount of distance it moves forward is exactly the same, is connected by the amount of angle it rotates. So let me show that properly. So that's your motion here. So that's S, and that's given by, this is your reference. So let's say this is your angle theta. And this could be your radius R. And what we are saying is that the amount of distance s traveled here is exactly equal to, so s is exactly equal to angle theta times the radius r. So that's a constraint we are putting. It could have been greater or less than this if it was slipping or if it was spinning around. Think of getting stuck in snow versus having a solid ice here and you're not able to rotate at all. There is no spinning motion possible when it is solid ice, and when there is no sliding motion possible when it is perfect snow. So those are the extremes, but a perfect rolling is somewhere in between. So we are assuming perfect rolling. So this is perfect rolling. If it is perfectly rolling, if we know the angular motion completely, then we can pretty much deduce what the translation motion will be, because they are all connected by this angle theta, connection between distance and r. So specifically, we will, so displacement, right? So time stays, so, or before that, I should say the axis of rotation here. So this is your rotation. Right? Axis of rotation is coming out of the board. Even though the axis of rotation is moving, the direction is staying the same. So in that sense, it is not going. So when I say axis of rotation will stay fixed, it doesn't mean that it cannot move. So what does it mean is that the direction of that vector is staying the same. It itself can move with the body. That doesn't matter. So in this case, the axis of rotation does stay fixed. It is coming out of the board. We do have time as delta t. So time is delta t. That's exactly like we had in translational motion. And now we want to talk about angular motion. So we will talk about angular displacement. Here we talk about delta theta. This is a vector in principle. It is actually measured with respect to the axis, direction of the axis. But if the axis is fixed, it is like motion in one dimension. Wherever things are moving in the same direction, we don't talk about vectors. It's only positive or negative. So similarly, delta theta is supposed to be vector, but since our analysis is going to stay simple, so that's going to, we will treat it as not a vector, just the magnitude is sufficient with the positive and negative sign in there. And that's equal to theta final minus theta initial. And similarly, delta t is t final minus t initial. If we want to talk about the angle theta itself, then final angle is assumed to be the actual angle theta. So we will say theta minus theta 0 at that time. So those are various notations. Once we have the displacement, we can define the angular velocity. This should be differentiated from translational velocity. At that time, it is translational displacement over time. And now we have, so this will be omega, and we'll define this as the derivative of theta with respect to time. So the rate of change of angle with respect to time. Once we have angular velocity, we can define angular acceleration. And that will be, we'll use the letter alpha for that. And this will be the rate of change of omega with respect to time, or this is also equal to second derivative of angle theta with respect to t. Physically, what this is that omega is, for example, angle theta is changing in this manner. It can go slowly, that is uniformly, but if it is changing, like for example, this is increasing in speed. So that's your omega measures how much rotations are happening around that axis. It can be uniform. That means if omega was uniform, it'll keep doing the same thing again and again. But it can change its speed. So for example, it can start getting faster and faster and then start getting slower. If the angular speed is changing with time, then you have what is called angular acceleration, and that's given in terms of rate of change of angular speed itself with respect to time. Often, again, because this is not going to change direction, it is okay to say angular speed also in this case. That's perfectly fine. But the correct definition will be angular velocity. When we were doing a translational motion, there was this nice feature where we could talk about uniform acceleration. And even though it's a simpler situation, there was a lot of richness in there. We will do the same thing in here. But before that, it is nice to notice that most of the time there is a connection between angular motion and translational motion, especially for a problem which involves a wheel that is actually rotating. And that's got by this quantity here. S is equal to theta r. If it was actually going only in this direction, in that case, I don't have to write S. Let me use that as X, right? Because then we will know how far it has gone in this direction. And but what is that X? That's the motion of the center of mass, right? How far the center of mass has moved, that is your X. And what we are saying here is that the translational displacement is equal to the rotational displacement times the radius r. So if I'm interested in the block, how far the block is moving, if I know the angular displacement, I multiply by the radius, I get the translational displacement. Just a scaling parameter in that, with of course with the unit of meter there. This is measured in radians, and this is in radians multiplied by distance. Remember, radians in this context is considered dimensionless. Even if it is in degrees, you're on a, so remember pi radians. So that the conversion is pi radians is equal to 180 degrees. And both radians and degrees, when it comes to SI units, should be thought of as dimensionless. That is just a measure of angle there, but eventually we don't write that down. If the angle is coming in open, not coming inside a function like sine or exponential, then you always want to work in radians. So it is expected that this is in radians. So it's necessary there. You don't have a choice that you can actually use degrees there. Same thing in here. Now we have omega, but the linear velocity is v, which is translational velocity. How fast is the center of mass moving as it is going down the road? And that's equal to the rotational quantity, rotational velocity omega, and you just multiply by radius r. It's kind of very convenient that way. In fact, in problems like this, when it is perfectly rolling, if you know the linear quantities, you can divide by the radius and get the angular quantities. Or the other way, you can get the angle. If you have all the angular quantities, multiply by the radius, you can get all the linear quantities. By linear, I mean quantities related to translational motion. That means as you're proceeding forward versus rotation. So there is a connection there, and that's because of the constraint of perfect rolling. Like this makes it how much ever angle it rotates, it has to move a certain distance due to that, right? So there's a constraint in that. And with respect to time, if r is fixed, then whatever changes happen here, it has to happen here also. So that's a due to the constraint, there is a one-to-one relation. What's the connection between acceleration? This is the acceleration in here, and that's equal to alpha times the radius r. Now, one should be careful in here. What do I mean by the acceleration in here? Which acceleration are we talking about? This is the translational motion of the center of mass itself. This shouldn't be confused with the centripetal acceleration. Typically, when there is a motion happening, there is also a centripetal acceleration that is towards the radius, right? For example, if I talk about what is the acceleration of this point, that it is moving forward, so there is a translation motion associated with it, but there is also an acceleration towards the center of the wheel, and that's centripetal. So here, by this we mean the tangential acceleration. So this is the tangential acceleration. Oh man, let me make it more precise. It's the tangential acceleration of a point at the outer rim. And why outer rim? Because this is the radius r, right? I'm using radius r. If I'm talking about any other point, I should know how far it is from the center of the wheel. So that's the connection between the quantities. But what is the actual kinematic equations if you are moving with uniform velocity? And there is a one-to-one connection again. And this will be a universal thing, generic thing we are going to see all through this rotational motion analysis, that there will be a one-to-one connection between what we studied already and between rotational quantities. So this was uniform like uniform angular acceleration. We earlier talked about a uniform acceleration. So here we are talking about uniform angular acceleration. Exactly like we had during uniform acceleration, and typically that's the first thing we do. So it hopefully seeped in sufficiently. And only if it is uniform acceleration, you can say delta theta over delta t. Notice this is not d theta over dt. This is the change in angles over change in time. Just for me, let me write this once. So this is theta final plus, theta final minus theta initial over t final minus t initial. This need not be d theta over dt. In general, the left-hand side is always true, but the right-hand side is not always true. Even if it is not moving with uniform acceleration, this is always correct. But the right-hand side, that this is equal to omega final plus omega initial over 2, that's not correct. So we will use this relation. Right, that's your definition for velocity, angular velocity, if you want, if it is uniformly accelerated. Only if it is uniformly accelerated. The other definition of angular acceleration, this is always true, and this will be equal to omega final minus omega initial over delta t. Actually, I take back, I said this is always true. No, it's not always true. Only if it is uniformly accelerating, you can integrate, and this says that it is linear in time. That's only true if it is uniformly accelerating. So both these definitions are valid strictly only if it is uniformly accelerating. In general, you have to either integrate or differentiate a given expression to get that. So it is a not very hard thing to do, but this gives you a lot of insight into what's going on. Again, imagine you have a wheel or you have some circular motion happening, and that's your angle theta here, and how fast it is going. So that's your omega, and alpha is the rate at which that is. But that's your two definitions. Using this, I can manipulate, right? I can add these two equations, I can subtract these two equations, or I can even multiply these two equations. And we did this analysis and while we were doing translational motion, and we can do the same thing in here. The algebraic steps remain exactly the same, and what we get is the following, right? So instead of linear displacement, so this would have been delta x earlier, this would be equal to omega initial times delta t plus half of alpha times delta t squared. Notice how there is a one-to-one correspondence. Delta x becomes delta theta. This becomes v initial becomes omega initial, and acceleration becomes angular acceleration. And rest of the interpretation remains exactly the same. And once you have this delta theta, and if this was a wheel rotating, then due to the constraint, you know delta x also. Delta x is equal to delta theta times r. So you know that also. We have, this is what we get if you add the, subtract the two quantities. If you were to add the two first and second equation, you get omega initial delta t minus half alpha, omega final, right? So this is when you subtract. If you were to add, you get omega final, and there is a change in the sign. So that is minus half alpha delta t squared. And finally, if you were to multiply these two equation, you get 2 times alpha times change in the angle. That's equal to omega final squared minus omega initial. I should again stress that here the axis is fixed, right? Axis remains fixed. Axis remains fixed. Particularly the direction of the axis remains fixed. The axis can move with the center of mass, that's okay, but its direction should stay the same. So that's an assumption that's going on, and only then you can get rid of the vector sign. So whenever you don't see the vector sign, so that's a clear indication that that is what is happening. So let's do a couple of examples, very much like earlier itself, except that we will work in the angular coordinates. And it is also possible that you can mix up things, correct? Because you have this relation, velocity is equal to omega times r. Let me not even write this as, so this is x is equal to theta times r, and acceleration, the tangential acceleration, is equal to alpha times the radius. And because of this connection, you can, instead of giving 3 quantities here, remember there were 5 unknowns, then we have to look for 3 given quantities, and there are missing variables. So this could be mixed, right? If I give you the radius of the wheel, and if you're talking about a wheel that is moving translationally, then I can give you the radius, and instead of giving the angular speed, I can give you the linear speed. And that is also a way of connecting with the variables. So let me do an example elaborating that. So let's talk about a wheel rolling wheel is rolling, is perfectly rolling. It starts from rest. That means initial velocity, right? It starts from rest and reaches a speed of let's say 5 radians per second in 3 seconds. And we could ask, what is linear acceleration? Find the linear acceleration. By linear, I mean the translational acceleration. So acceleration and given radius is equal to 1 meter. Let's say. So 1 meter is a pretty large wheel we are talking about. It doesn't represent the wheel of a car or truck. 1 meter is almost almost half of a typical human. So what are the quantities given? Omega initial, let's say delta theta, delta t, omega initial, omega final, and alpha, right? That's your 5 variables you can think of. And omega initial, it starts from rest. So that's omega initial is equal to 0. Reaches a speed of 5 radians per second. So that's 5 radians per second. And what else is given? Delta t is 3 seconds. So that's 3.0 seconds. So that's your 3 quantities that is given, but it is not the angular acceleration that we are interested in finding, but instead it is a linear acceleration. So the idea is that first find this. So this is what we want to find, but we are interested in the tangential acceleration at, which is alpha times radius r. So that's what we want to find. And this is your missing variable. So you would look for, in the 5 equations that I wrote down, you will look for the quantity that does not have delta theta in it. And it turns out to be the second equation. So that's alpha is equal to omega final minus omega initial divided by delta t. That's equal to 5 minus 0 divided by 3.0. So that's 1.7 radians per second square. And acceleration then is alpha times r. That's a connection. So if it was just angular motion, you would be satisfied with this, but we are converting this from angular to linear motion at this point. And this is equal to 1.7 times radians per second square times 1 meter. And notice that when you switch that, you drop your radians, right? Radians is, it has dimensions, but in the SI units, in that context, we don't mention the radians. So this is 1.7, and now it becomes meters per second square. We drop the radians. So angles is considered dimensionless in SI units. That's good. So this is one example. Let me quickly do one more example, and let me do something with angles so that we know how far the car has gone. So let me do exactly the same problem. A wheel is perfectly rolling, but let me give you the distance, and which will require that it be converted into radians, and it has to be used. So. So, same example of a wheel. And this time, so a wheel is rolling. And so let's say starting from rest. It covers, let's say 5 meters in 2 seconds. And the question is determine the final velocity. By final velocity means at 2 seconds, what is the final velocity? Again, do the same thing as delta theta, delta t, and omega initial, omega final. This is equal to 0. Right? Omega final is what we are looking for, and angular acceleration is not given. Time is given to us to be 2.0 seconds. It seems like we are given only 2 quantities, but notice that this is distance, right? Distance means that you can convert it into angles. So what we will do is, first thing we can do is convert that. So delta theta, so delta x is equal to r times delta theta. So delta theta is equal to delta x is 5 meters. Oh, I should have given you the radius also. So radius, let's again say is 1 meter. So that's 1 meter. Notice distance over distance, that comes out to be dimensionless, but we are talking in terms of angles. And this now, since we don't write any units here, this could be a little confusing as to what is the units here. How do I know that it is radians or degrees? Whenever an angle shows up in an equation in an explicit manner, it has to be always in radians. It is necessary that even if you're given the question in degrees, you have to convert it into radians. So always work with radians when there is an explicit delta theta showing not inside. For example, sine of theta, it doesn't matter whether you use degrees or radian as far as you use your calculator in the right manner. But here it is necessary that you have to work with radians. Temporarily, if you want to convert it into degrees, it's okay, but you have to come back in the expression, you have to put things in radians. So this is 5 radians. And how much is a radian? Remember that this is 2 pi. So when the full circle is 2 pi, so that's 2 pi is about 6 radians, right? So 6 radians is approximately 360 degrees. So how much is 1 radian? So that's about 57 degrees. So it's a good thing to remember that. So this angle is your 1 radian. 6, approximately 6, because 2 times pi, right? So this is 2 pi radians is 360 degrees. Pi is 3.14, so 6.28, right? So 6.28 radians is 360 degrees. So divide this by about 6 and you will get about 57 degrees. So 57 degrees is approximately 1 radian. So just to have an insight, that's always useful. So that's 5 radians length. So now we know angle delta theta. So that's 5 radians. And now we have three quantities, 1, 2, and 3. We are interested in omega final, and that's your missing variable. And if alpha is missing, so then you would go and use the first expression, first equation in the list of equations that we were having. So that's delta theta pi delta t is equal to omega final plus omega initial over 2. So that's 5 radians. Let me write it explicitly. So it's 5 radians over 2 seconds. That's equal to omega final plus 0 over 2. So 2 and 2 cancels, so omega final. So omega final is equal to 5. 2 and 2 cancel, second does not cancel, so it is 5 radians per second. That's your final angular speed, but we are looking for the final velocity. So whenever, if I want to be more precise, I should say this is translational velocity. So translational velocity V final will be equal to omega final times the radius r. See how I'm going back and forth from translation motion to angular motion. And that's equal to 5.0 times, let me again write the units so that it's clear what I'm dropping. So this is equal to 5.0 radians per second times 1 meter. So this will be 5.0 radians meter per second, but you drop the radians at this stage. So when it comes to translational quantities, you forget the radians, but when it comes to rotational quantities, you keep the unit radians. I'll stop here. So there's two or 3 minutes left, but I'll stop at this point. And we'll come back to the idea of torque next time. I don't want to start that now. Thank you.
Have a good night.
You too. Bye.
Goodbye.
Mm-hmm. Let me end the meeting if there are no questions.